Naboda is here. In part 2, we started defining our 7' component archetypes and their attributes. In part 3, we'll finish that and get to the individual pipelines. This is Modularity, part 3. Well, that's enough for preamble. Let's get right to it. Shields are the least developed component at this stage, because devising a system for shields is not really necessary at this stage of the example. Shields for the nonce are either on or off. We will account for them in the ship pipeline with placeholder values and have them draw power, create heat, and of course generate shield. We'll need these to be at least accounted for because if we continue with this example, we'll need something to stop bullets and stuff. Mostly they're here because in this example they have a lot of mass, generate heat, and eat power, so I wanted to have them around so I could at least ballpark every other component's numbers right off. Cooling systems are integral to all vehicles in space and are a combination of advanced old technology and centuries-old breakthroughs in thermoelectric manipulation, so it's not all pumps, pipes, and ammonia anymore. Heat is constantly being arranged throughout the ship to keep all components functioning properly. An abundance of heat is the result of compact and very powerful components at work. Coolers use power to actively cool, or deliberately transfer heat from the heat pipeline and radiate it out of the ship. Cooling is reducing heat. Regulate is the passive function of coolers, as they run a thermal loop throughout the ship, which is actually sustained by the heat the cooler is managing. Active cooling uses spin, but regulate functions instantly and directly with the heat pipeline. The value for regulate is how much heat can be pulled from components and transferred to other components, the whole at large, or moved to the coolers for active cooling. Heat still takes time to move in the pipeline, but regulate determines how much and how quickly. Intakes are the wild card of components. More thermoelectric, electromagnetic, and electrostatic field manipulators, the intake's primary function is doing the most with as little as possible, but we'll discuss the lore of achieving impossibly improbable feats that became mundane 500 years ago outside of system building, perhaps sometime in our future, right after a little more lore. Intakes are essential for modern space travel in that, minimally, they subdue the ionic barrage inevitable while traversing star systems. This function was redoubled by the advent of shields, but was also already necessary for the perpetual function in quantum drives. Intake is the first attribute. The value of intake is burn mitigation. Intake does not create fuel, but provides pre-accelerated particles for reaction mass, and intake substitutes fuel for burn. Intake requires power and generates heat. Intakes are limited in the particles they can process. Even if the particles are available, the intake can only manage so many. As they are designed to make the most of the least, they have a very low saturation point. The kinetic attribute is taking advantage of that saturation point. While it is much more efficient to use intake in concert with engines to create force by mitigating burn, kinetic can be used as an additive to an engine's force by saturating the intake static net with a trace amount of fuel. The burn for kinetic is insignificant, but without the engines running at 100% to facilitate this, the cost to force ratio is hard to justify. Kinetic consumes power and creates heat. Intakes have a third function in which they use power and heat to create thermoelectric pockets that mimic heat convection in vacuum. This makes the intake function much like an atmospheric heat sink, and is another option for ditching excess heat in a pinch. Items and attributes are something every gamer is familiar with, whether the items are based on a system or not. So most of the last 5 minutes was the same old routine of saying what something is and what it does. We try to give logical attributes and values to things because they need to fit together believably. My shoes don't make me stronger, but we might say that they cause me less fatigue by protecting my joints from stress, and allow me to get around better in rough terrain. This is the difference between a simulated universe and your run-of-the-mill game type of game. So we need all of our parts to work together with shared and unique attributes that result in some intelligent combination of parts to get something done in a way that makes sense. Your answer to low acceleration might be just to pile on bigger engines, but another player's answer might be more efficient engines with less force, but less consumption. Then they balance out their components with other low-mass components that have less engine to feed and support, and end up with less mass and just as much or more acceleration at lower cost. The problem with this route is that the ship produces less to do more with other parts, while the bigger is better has more options when considering other functions that require resources, and it is affected to a different proportion when adding more mass. We'll get to this more later, but these are both examples of ships from our system, with just a couple of key points of information. We're going to go over the pipelines individually, but let's put together a starter Aurora so we can go over the pipelines in the testbed for the ships. This is a first pass dirty sheet. It's all data, so if numbers aren't your thing, you're not going to like me very much in a few minutes. All ships work from the same template, otherwise there's no point in a volumetric standard. The first thing we do is record what we're making, Aurora Starter. A starter ship should be just that, enough to get you started. It's describing the loadout as being a starter loadout, but the hull is completely modular, meaning we can change the components to get 101 different ships. The Aurora isn't a starter hull because it can be arranged to be very capable within its component allotment that we designated in Part 1, but we'll build it to be very easy and safe to fly. Let's grab the hull stats and start populating these fields. There. Now, let's see what space we have for components. This is what we can equip, and this is what we have equipped. Let's grab a Volume 1, Size 1 power plant and install it. We've got 6 volume in 2 places on the hull for batteries, so we'll be modest and take 2 Volume 3 Size 2 batteries. We have 8 volume for an engine, but it's a starter, so we'll go light here too, and install a Volume 3 Size 2 engine. We'll go ahead and give it a full load of thrusters, so 6 Volume 0.5 Size 1 thrusters, a modest Volume 3 Size 2 shield, but we won't cheap on the coolers, so we pretty much can't run into trouble there, because it's a starter. Finally, we'll do 3 Volume 3 Size 2 intakes, and see what our generic starter looks like. Here's the hull's mass from the hulls we baked in Part 1. The total ship mass is showing at 11,500 kilograms and change after we added our components. We've added mass for crew stations, avionics, life supports, and fuel, and we can add more mass for stuff if we want to see how adding things like weapons will affect the ship's speed, maneuverability, and operating range with hardpoints and cargo. In ETO, we can see the maximum force available to the ship. We did a few things here. Top speed is determined by the IFCS by available acceleration dynamically. My top speed is 0 because my acceleration is 0 until I start the ship and spin up the engines. In this example, small ships with small components are very reactive. Most of our components will spin up fully in a couple of seconds. Let's fire up the ship and see what happens. The time lapse will tell us how many seconds have passed, which I can trigger at any time I want changes to update. On the control board, I tell the ship what to spin up or down, and can also tell the heat pipe which loops in the system to have open or closed, increasing or reducing heat distribution throughout the hull. The power pipe will keep track of my output and distribute it to components asking for power. The capacity pipe will turn excess output into charge and send that to capacity. We'll get to heat and fuel eventually. Let's just get this puppy out of the hangar, which is going to take some imagination, but something like this will be happening every time you sit the seat in Star Citizen, just so you know. We spin up the power plant and lapse a second. The screen flicker is the sheet running through numbers, so whenever you see that, a second in the system will pass, and time lapse will update to tell us how long it's been since we started. Since I have no components asking for power, the capacity pipe will start charging its capacity. I deliberately made charge a very high heat cost, so we'll need to fire up the coolers. We deliberately overcooled our starter ship so we wouldn't have to worry about heat, so we'll throw 10% spin at the coolers and see if that keeps us all cold all around. Let's get the batteries fully charged before we take off. We'll crank up the power plant to 100% so more output is picked up by charge, and this will start heating up the hull a bit. There's no AI active, just logic, so if we see heat creeping up, we have to regulate and add cooling by increasing spin to coolers. Okay, capacity is about peak, so let's back off the power plant, light up the engines and thrusters so we can move out. Okay, with 23 meters per second acceleration, the IFCS says we're allowed 89 meters per second top speed, and our strafe acceleration is 15 meters per second. I didn't figure in yaw, pitch, or roll. We know how this works for Marina Commander, and for a dirty example system, we don't really need those per hull. What we have is a ballpark for strafe acceleration. While it isn't exact for each hull, it'll always be pretty close, so we're going with that to give us an idea of maneuverability hull to hull. Let's add some throttle in ETO and get out of the hangar. Our velocity will update as engine force is applied, which will run up the power and heat cost a bit, but at 50% spin, this is almost nothing. As our fuel store is reduced by the power plant, our top speed will continue to increase slightly, because as we shovel out fuel, our ship is reducing mass and increasing acceleration. We're at 10% throttle and 8.9 meters per second. We don't need the power plant spun up so high because we're not using much power, so let's kick the engines up to 100% and see what the starter can do. So without weapons, but with fuel, our starter Aurora has about 47 meters per second acceleration and 167 meters per second top speed. That's pretty close to what we have in Arena Commander, so we're lining up okay with the numbers. Let's starter out the engine just a little more. and reduce it to a volume 2 size 2 engine. 32 and 119. Let's grab a volume 2.5 size 2, 40 and 144. Well, it's ballpark. Okay, now that we see that there's a simple and working dirty system, let's go through the pipelines pipe by pipe so we have a better idea of what's happening under the hood. All we control in ETO is our throttle and boost. Just like in Arena Commander, whatever we set our throttle to is basically asking the IFCS to keep us at that percentage of our top speed, but we ultimately control our top speed by the spin on our engines and thrusters. For a small ship with small components, it's practically instantaneous, but a small ship with bigger components starts incorporating the need to consider what is going to happen, instead of just what is or already has. We can also set a percentage for frenetic, which just emulates frenetic flight, so it'll calculate engine and thrusters as if they were maneuvering the ship, instead of just firing engines when we accelerate and thrusters when we retro. Typical combat would be 60 or 70%, just flying in a circle with everything pegged would be 100. The left trigger for boost is whether to activate boost prime when the engines are at 100% spin, and the right trigger is afterburn. The boost cruise is available when the prime is complete, and basically tells the IFCS you have a full prime for afterburn and would like to be allowed a higher top speed. Triggering cruise will continuously prime, spending the prime rate each second. There's no such thing as a free lunch. The power pipeline distributes power to components. It doesn't store power. It can only send out as much power as it receives from output. Any extra output is routed to the batteries, which charge their capacity. Batteries are limited in charge and capacity, so having more output than the power pipeline can send to other components or the capacity pipeline is just wasted output. We spin down the power plant a bit. The capacity pipeline is just a battery network. As the batteries charge, the ship has access to additional output when the power pipe is overtaxed due to heat, having too many components overspun, and drawing more power than the power plant's output when the power plant is offline due to damage while it is spinning the quantum, or just having the ship deliberately run on the capacity pipe, possibly to skirt unwanted attention. Output from the capacity pipe has a very small effect on the power pipeline signature. I'm all out of time, so that's it for this video. Next week, we'll pick up where we left off, finish running through the test sheet and pipeline so we're all on the same page as to how the Prime 7 components fit together, and hopefully get back to the archetype and filter system. See you next Sunday. As always, thanks for your time. Neb, out.